Singularity.
My name is Nikola, aka Socrates, and you're watching Singularity One-on-One. Singularity One-on-One is a regular podcast of Singularity Weblog, and if you guys enjoy this show, you can help me make it better by either liking this video on YouTube, writing a brief review on iTunes, or by simply making a donation. As always, I will be the man with the questions, and today my guest with the answers will be Professor Danko Nikolic. Danko Nikolic is a brain and mind scientist running an electrophysiology lab at the Max Planck Institute for Brain Research, and is also the creator of the concepts of ideasthesia and practopoiesis. Thanks for taking time to be with us, Danko. I'm very happy to have you on my show.
I'm also very happy to be here.
Danko, let us begin our conversation today by asking you to please introduce yourself and what you do for those of our viewers and listeners who may not be familiar with your work.
So I'm initially by training a psychologist. I studied psychology in Zagreb, Croatia. Then I moved to the United States where I got a PhD in psychology. And after having studied psychology for so many years, I realized that the time was to begin studying the brain, the physiology. And that's why I moved to Frankfurt in a neurophysiological laboratory. And over years, I've been studying both sides, psychology and the brain side, which allowed me to understand both sides and to develop theories of both sides and also theories how the two are related.
That's absolutely fascinating. So let me ask you, are you a psychologist then, first and foremost? Are you a sort of a cognitive neuroscientist?
I think cognitive neuroscientist would be the closest description.
And what would be the difference? Enlighten us, the poor ignorant souls.
Well, a cognitive neuroscientist likes to look at the both sides, the psychologist side, but also at the neuroscience side. Whereas a psychologist would typically just look at the psychological part, the mind. Well, the cognitive neuroscientist is trying to make a connection between the mind and the brain.
Mm-hmm. So now, making that connection between the mind and the brain, I have interviewed a few neuroscientists who have said that the mind is the brain, that there is no necessarily that kind of dualism or that kind of mind-brain gap is kind of an artificially created one. It's not the real one, that the mind is the brain.
Well, that is certainly, in a way, truth. Nobody believes today, or almost nobody believes today, that there is a special spirit added to the material part of the brain. However, we still use this difference, and it's very useful distinction between these two terms, because in one term, the brain term, we refer to the physiological mechanisms. And then when we use the mind, we refer basically to what this whole system does together in action when it's put together, when it's fully functioning and doing its own thinking things and experiencing things.
Mm-hmm. And how did you get interested in first psychology and then cognitive neuroscience? And why do you think that's important? Tell us about your journey of getting there, personally speaking.
Well, my personal journey is, I think, very interesting. When I was somewhere in my early 20s, when I had no intention to be a brain scientist, research scientist, but I had wide interests and wanted to read all kinds of different books about different things in the world. And one day I decided to go in the library and get a book on how the brain worked. I just thought, it would be a good thing to read that book and know a little bit more about it. So I went to the library, couldn't find the book. Then I went to the other library, couldn't find the book again. Took some research to realize that this book was never written because no one knew how the brain worked. This was a surprise for me at that time. I was maybe 21, 22. And then it really, made me curious. Why do they don't know how the brain works? Why is it so difficult? That's something interesting to find out. And I got reading more and more and more and got hooked. And you get hooked on some things that you can't really stop doing them.
Mm-hmm. And then you decided to perhaps write that book yourself?
Yeah, in a way. I haven't still written it, but Maybe one day.
But you're working on pieces of it, right? You're putting the pieces together.
That's right.
Very interesting. So what is the ultimate goal of your work then? The best case, the dream scenario is that, let's say after 20 or 30 years, after a career in the field, you have the manual of the brain. Here's how the brain works, manual.
Yeah, I'm not imagining it as a manual or some sort of a technical scheme that you get with some, let's say, electronic device where it's, all the pieces are there listed out, specified, and so on. But more like something like the role that the theory of evolution plays for biology. Compare biology before the theory of evolution and after the theory of evolution. So if we had some theory like this about a brain-mind problem, something that's as powerful, as insightful, but of course doesn't provide the details, just provides the basic, most important rules of how the matter transforms into the mind. I think that would be a really great thing to have.
Mm-hmm. And yeah, I mean, the theory of evolution was absolutely seminal and sort of groundbreaking, revolutionary, not only for the field of biology, but also for a number of other fields. But so is your theory of practopoiesis then that theory of evolution? And what is practopoiesis anyway?
Well, practopoiesis is a theory about how adaptive systems organize, how they function. And the biological systems are adaptive systems. Our majority of adaptive systems that we have in our world are biological systems, and there are a few other technological ones, but biology takes the biggest part. And practopoiesis is an attempt to create a theory of how such a system would be organized, such that we could understand its internal functioning, even though the system is extremely complex. It contains billions of components. But if we have the basic rules by which it is organized, we may understand that. Again, we can make a comparison to the theory of evolution, which is describing a process that's extremely complex. It's like billions of years of process of molecules interacting on the entire planet Earth. It's no way you could make ever a computational system or process to describe that. But with a very small number of rules, it's like 3 rules or something, you can actually describe and understand much of this process, what has happened. Of course, you cannot predict the details, you cannot explain exactly what happened, but it's extremely helpful. So practopoiesis is a similar attempt, but not to understand how the organisms evolve, but to understand what happens to an organism once it has been born or conceived, right? How it's organized internally. And it turns out that these two theories are actually quite friendly to each other, quite similar. And in a way, theory of evolution can be understood as a special case of practopoiesis.
Very interesting. And what's the actual meaning of the word practopoiesis?
It comes from ancient Greek. The word praxis indicates action, and the poiesis indicates creation. So it's a theory of creation of action. So the basic premise is that biological systems have the function that they have because they contain a large number of small units that are able to act in some adaptive way. They have a knowledge on when to do something about the organism and what to do in that time. So this is an action that these units perform. Now, the question is not only which actions these units perform. That's an important question. That's what biologists do all the time, of course, and a neuroscientist looking at a neuron, what to do. But the key question in practopoiesis is, how did this action come about? Who created this mechanism? Who created this machinery? And it turns out that this is basically other action mechanisms at another level of organization that by its own actions create action units at a higher level of organization. Right?
Mm-hmm. So basically the question you're trying to address here, the way I understand it, is how do we create or how do we take actions? Is that correct?
I would say the question is, which mechanisms have enabled us to be able to perform actions? Yeah. If you have any system that you describe, you may describe a system of how some inputs come into our body and how some outputs come about. And you could describe the system. But there is always a question, who created the system? How was this system put in place exactly such to perform these actions? Practopoiesis is a theory of creating systems.
Mm-hmm. Mm-hmm. Very interesting. And so then tell us a little more about the theory. Try to sort of lay out your answer to that question. How do we do that? How do those systems evolve or come to be?
So the basic premise of Practopoiesis is that these action units are organized into hierarchy. That for any action unit that has been produced somewhere through a biological process, there was some other action unit lower on the hierarchy that acted with its own mechanisms, interacting with the environment, of course, and by doing this process has created the properties of the unit at a higher level of organization. Now, this unit at a higher level of organization can again interact with the environment and produce a unit even higher at the level of organization. So we have, for example, at the lowest level of organization, we would have evolutionary mechanisms that create the properties the genes have. Now, in an organism, you have expression of the genes and the gene expression mechanism, which is a higher level of organization, which then produces the anatomy of the organism. Let's say this produces the anatomy of a nervous system. Then the anatomy of the nervous system forms a mechanism that interacts with the environment and produces our behavior. So we have here a clear hierarchy, which is a poetic hierarchy. One mechanism creates the other mechanism, which creates the other mechanism. And the theory formalizes this process in a number of steps and makes it understandable how things interact, what are the requirements, and puts everything in the framework of so-called cybernetic theory, which is very useful.
Mm-hmm. So give us a couple of sort of observable cases or examples of where sort of we can fit examples, be it from the animal world, from the machine world, or from us, and how do we fit within that kind of a hierarchic sort of model?
Okay, it's so I already mentioned the example with genes making the structure, but in general, in neuroscience, what we have realized so far is that the neural network requires so-called plasticity mechanisms, and plasticity mechanisms are separated units, separated tools, separated molecules, separated equations in any model that operate on their own, and by doing so, change the properties of the network. That would be a biological example that is very well studied and quite well understood, right? But also in technology, we have a similar example. For example, in a classical neural network, you would have a level of network of neurons which receive certain activation, have synaptic weights, they interact, send information to each other, and at the end they produce output. That's the higher level. But the architecture of that network matters very much because depending on the architecture is defined the function of this network. Who creates the architecture of the network? These are the learning mechanisms. So machine learning theories are basically about these two levels, require you to develop some sort of a system that will interact with your data and some sort of system that will learn how to interact with a particular data set. Right? So we have two levels of organization. Now, by developing practopoietic theory, we can ask very interesting questions, like what happens if we don't have just two levels, but what happens if we have three levels or more levels? Can we make an even more adaptive system? And also a very interesting question, is it possible that our nervous system, that our mind, our brain are organized with more than two levels? So far, all the theories that I know of are thinking about the brain as having these two organizational levels. But using practopoietic theory, we can think through what happens with three organizational levels and ask the question, is that maybe how the brain works? And it turns out my proposal is that yes, it is. We need three levels.
Mm-hmm. So tell us a little bit about the sort of the interaction of the levels and the benefit and the costs of having three levels hierarchical organization rather than, let's say, two or a single level, but which is very sort of broad sideways rather than hierarchical. And how is that going to change on the sort of dynamics of the system?
Okay, that's a very good question. If you have just one level, let's consider just one level. You have a system that has all the knowledge on what to do already prepared in it and just responds immediately. This system is going to be very fast. Doesn't have any time to learn. It just knows immediately everything. So the great advantage of having few levels is speed. The great disadvantage of having a small number of levels is the requirement of the memory or the capacity system that you need. You have to have pre-stored all the possibilities already in the system. So if you don't have all the possibilities in the system, then if you cannot fit them all in the system, then you have to miss out on something. Now, if you have multiple levels, then what an additional lower level can give, you can adjust the upper one. So the upper one can be prepared for a given situation, for a given world. That's what we do, for example, in machine learning algorithms. You don't make a computer program that will recognize all possible images, all possible objects, and do all possible actions. You actually train it for a certain particular data set. This reduces your requirement on the resources. Now imagine you had a third level where you don't even have to learn. You don't even have to how to say it. You don't have to program your learning mechanisms for the upper level, but also your system can learn this learning mechanism. So all your program is like 2 levels below, and then the system learns how to learn, basically. And what you get with this as a let's say disadvantage, first, the system becomes even slower. But as an advantage, what you get is the system gets even more adaptive. It can adapt its learning. It can learn how to learn. And the key idea is that our cognition, our cognitive process, is basically application of this system, of these learned learning rules. When we think about something, when we solve a problem, when you recognize something, any operation, any cognitive operation is not just information processing at the top level. In addition, it's a process of reorganizing the system, reorganizing the network through the rules of you have learned how to learn.
Mm-hmm. So let me ask you a couple of questions here then. So first of all, it seems to me that then another disadvantage of the multi-layer or multi-hierarchical system would be the requirement, not only that it has a slower speed of response, but also perhaps higher requirement of resources. Is that the case?
Actually not. It has lower requirement on resources.
Why is that?
Because you have you solve the combinatorial explosion problem. Right? Imagine you have to produce an artificial intelligence system that has just one level. Then, in that case, you would have to program in this system all possible cases, problems, questions that this system will ever be asked.
Mm-hmm.
That's not possible. You may need to require, a computer of the size of the universe for that, right?
Yes. So by going multi-level, you actually improve the level of efficiency because of the combinatorial possibilities of the multi-level.
And these combinatorial possibilities are always used, and new combinatorics is produced through interaction with the environment, through interaction with the current situation in which the system is interacting with, right? So you don't have to be prepared for everything. You're just prepared. You have your general rules, and use these general rules to change your system according to the situation in which you are finding yourself right now.
And now you say that perhaps the human mind is a 3-level sort of model.
Yes.
Now, what is there a way to test this? I mean, I'm just trying to see how do we falsify your hypothesis? Is there a way to?
I think so, yeah. There's a way to falsify this hypothesis. We can make predictions about how a three-level system should behave. We can make a direct comparison between how in a certain situation a three-level system should behave and how in a two-level system should behave. And for example, a three-level system should, in a novel situation, should take time to readjust. The more novel the system, the more time it should take before it starts doing something, acting something. While a two-level system would not take time because it wouldn't even have a level that would say, hey, slow down, I don't get this, we don't know how to do this. Now, what two-level system would do, it would start making instead mistakes, errors. When something new happens, when some new situation occurs that it didn't experience before, it will make errors, it may adapt to it slowly, but it will first make errors and then adapt. While a three-level system may actually not do anything for a while or just play a little bit with the situation, think it through, and then start producing actually correct behavior. So T3 system would behave, actually would produce correct behavior quicker, although the first behavioral acts would take longer. Whereas a two-level system would quickly respond, but incorrectly if the situation is. And now it turns out that when we look at human behavior, it's exactly what happens. There is in psychology a well-known phenomenon of a change from automatic to from controlled to automatic processes. And a good example is when you do something complicated, some skill for the first time in your life. It's very slow. It's very difficult.
Like playing the piano, for example.
Yes. And after a while, you practice, it becomes faster and faster, and so on. Two-level systems don't have this property. They learn equally quickly. Once they learn one thing, like playing a piano well or playing a certain piece well, they do it really well. But what they have a problem then is that if you teach them a new piano piece, they will forget the old piano piece. It's called catastrophic interference problem in neural network. Right? Three-level systems don't have this problem because they never memorize exactly how to play a certain piece or how to do something precisely exactly. They store all the knowledge at one level lower, at one level more abstract, and then each time when you have to play the piano, you have to basically use this abstract information and reboot it, reorganize it, use this poetic process to reorganize your network in order to prepare yourself. And then it takes time. If you didn't play piano for a few months, you cannot just jump and play. You have to prepare a little bit, try something, and then you can play. Three-level system does that. A two-level system, no, it goes straight for it, makes no errors, or it makes irreparable errors.
Okay, so that's a necessary evidence to support your claim. Is it sufficient though? Because here's the next question that I have. So obviously a two-level system will be faster but would be more error prone than a three-level system. But does it mean that three-level system would do no errors? I mean, no. I just imagined it would be less prone to doing errors and it would take longer time to react. But still, there will be errors made, and there will be time. So the devil is really in the details. So how do we know how many errors, percentage-wise, take us from level 2 to level 3, and the speed diminishing take us again from level 2 to level 3.
Yeah.
So you got me along on the necessary. Now take me along the sufficient path.
I think that it's not. It's a type of error you make. So each system would make a different type of errors. Let us just remember that it's human to make errors. And so if we are at three-level systems, well, we do make errors. Now, what type of errors do humans make, and what type of errors do machines make? Compare these two. Humans make errors of, let's say, vigilance problem. They are doing good, and then once they mess it up completely, and then they correct, come back, okay, I messed it up, I lost my attention, I don't know what happened, and then you go back and do things well, and then again you mess up. Now, at 2-level, our machines, which are up to 2-level, don't make this kind of errors. What they do, what they are programmed for, and what they are designed for, they do really well, better than humans. They don't make these mistakes that humans make. But their type of error is that they cannot adjust anymore. They cannot adapt. They cannot come up with a better way to do it. They cannot come up with a better idea on how to do things. Now, there is this mechanism in us humans behind its work. Well, I'm quite good in playing my piano sonata right now this way, but then there's this mechanism behind thinking of better ways to do it, novel ways to do it. And this same mechanism that is, eventually produces creativity and so on, and can make you compose a new piece, it's the same mechanism that makes you sometimes make error and you miss a note or something by playing your well-trained sonata. And that's these comparisons, I think, are crucial to understand the difference between 2-level and 3-level systems.
Mm-hmm. Is there 4-level systems?
Yes. You take, if a human or any animal is a 3-level system, it's an individual. A species itself, the entire species is a 4-level system, because the 4th level, the lowest level of organization, is the evolution. And the species has this additional property of evolving. And we humans don't evolve, but the species evolve. This is another adaptive level that an individual doesn't have, but in our species has this additional adaptive level that it can evolve into some other species even. So there are 4 level systems.
So the higher level of sort of poiesis is taken from the individual to the collective over long periods of time through the period of evolution.
Can you rephrase that to make sure that...
Yeah, to make sure I get it right and I communicate it right. So the higher level of sort of learning... no, I'm trying to find the right word here, and I
that capability?
Yeah, yes. Okay, yes, or flexibility in a way, really. Yeah. Intellectual flexibility in some way, or knowledge even, is taken one level higher as an abstraction from the individual to the collective level over a long period of time, where the learning is kind of encoded via that process of evolution.
I think I would agree with you, but maybe we would need to sit down and rephrase it differently. But yes,
how would you say it better than me?
The species is more adaptive than an individual.
Yes.
Species contains all the adaptability of individuals, plus has an additional capability that no individual could ever achieve. You just go and die, but your species can go further and become...
Yes, so a species over time is more flexible to adaptation than an individual at a single point of time.
Now you got it.
Okay, I took some struggle. Okay. All right, good, very good. So we're making progress on this end of the microphone too then. Okay, so... and is there then the next question is, so if that's the 4th level, is there a 5th level?
In theory, one could think of it. I have no any insight of understanding how 5-level system would work and what.
Cosmologically, maybe.
Maybe cosmologically, what some people have proposed to me is to understand the society. So the other the other end of the dimension, right? So individuals combine and interact into society, right? And there's a possibility that there is maybe an additional level somehow in the organizations, in the, let's say, in the companies and organization, a group of people is an organization. But I just did not spend enough time to understand this properly. So I cannot really, I don't know right now whether this is really new poetic level of organization or not.
Yeah, I have to agree with you. I can see how some people would say that, let's say, a bureaucratic organization such as a government or a corporation would kind of encode that level, that knowledge at another level of abstraction. Yet I'm not quite sure if it really fits. I would need a little more convincing or figuring out how exactly it plugs in there. But you know what? This kind of reminds me a little bit to the Markov models that Ray Kurzweil talks a lot about in his book. So is that similar or different? Would you help us make a distinction?
I think it's very different. Markov model itself is a one-level system. It's a mathematical system that has equations. That is, let's say, a lower level of organization. And then you have, you apply these equations, they calculate something, at the end you have some numbers coming out of it. That's the operation of at the higher level. So you have this operation produced from low level to the higher level. You may have some other mechanism that gives parameters to the Markov model. This could be a learning mechanism. So we would have one level Markov model, the other level would be learning mechanism. So as far as I understand it, it's still a two-level system. And it still have all these limitations of two-level systems. No matter how intelligent and creative you are in coming up with the algorithms, with the equations, with the system for learning, if you are at a two-level, then you will be limited. You will stay at these limitations.
Mm-hmm. So I'll come back to that in a second, but before that, let me ask you this. So how is Practopoiesis going to help us, for example, in the creation of artificial intelligence, or will it?
I think it certainly will, because it's basically telling us that what we do right now with machine learning algorithms, with neural network algorithms, is not going to be enough. We can produce more of those algorithms. We can build bigger machines, but they will grow only, as you said,
sideways.
They will contain more and more knowledge. They will be better than humans in this knowledge that they have. They're like Watson computer. They will have a huge amounts of really fast access to information, but they will never have this third component of adjusting, of coming up with new ideas, of being creatively thinking about, okay, but I could now improve and come up with something even new. Now, this is not a critique, like, you are never going to do it. Actually, Practopoiesis is telling us what we need to do, what we need to think about, in which direction we need to go to make it human-like type of adaptive intelligence. We need to have three-level systems, and which, by the way, in the theory I call it T3 system. And that's where our engineering efforts have to go. So we should not think of learning mechanisms for these algorithms, for these machines. What we should be thinking of is the mechanisms for learning how to learn. So go one level below and come up with mechanisms for learning how to learn, and then let the system learn its own learning, so it learn its own learning rules. At the end, what turns out is that all our knowledge is then becomes stored in these learning rules. Now, that's very different than what we have now, what we have traditionally. Now we consider, for example, in the brain or in artificial neural networks, we think that knowledge is stored actually in the anatomy of the network, in the synaptic connections, right? In other machine algorithms, you have a parallel to some other matrices where information is stored. And then you have interaction of some systems, some equations that deal with this, with these numbers stored in these matrices. However, what Practopoiesis tells us, no, this doesn't matter. You need all this system. Of course, it's necessary, but that's not really where the key is. The key is one level below. And our actually human knowledge is stored in the rules on how to learn. And these rules are applied quickly within, let's say, half a second, 1 second, couple of seconds. When you perceive something, you reorganize your network through these learning rules. So we have over life, we acquire, huge amount of learning rules. And to acquire them, we have a small amount of rules even below them of learning how to learn. That's the way how we have to engineer and how we have to think.
So big data is just not enough.
Big data is not enough. No, not at all.
Because some people think it's a matter of number crunching. Like once you get to a certain level of data, then you get qualitative transformation simply due to the vastness of that data.
Well, this is in principle correct, right? You could have, in theory, a two-level system, a T2 system, that has all the necessary knowledge. It doesn't have to adapt. It has everything already in the network. It's just when you look at the combinatorics of it, it's just going to explode. You're never going to have a big enough computer to store all possible situations in which a human could encounter. Right? This would mean all possible lives, all possible worlds, all possible languages, all possible everything. It's never going to be enough memory for that. You have to go one level more abstract and have some generalities, and then from situation to situation, from moment to moment, adjust it very quickly. This could take half a second for us, a couple of hundred of milliseconds. When things is more complicated, maybe a little longer. When something is really surprising, takes a little longer. And but that's how we do it. Basically, our consciousness is the process of this restructuring, continuous reorganization of the system.
Mm-hmm. Now, you mentioned one word there that I want to grab, but before that, I want to ask, it occurs to me that may be actually a useful way to differentiate between narrow AI and general AI.
Yeah.
Like, narrow AI would basically be restricted to 2 levels maximum, whereas anything above that would be general AI.
Yes, that's true. Actually, if we look the history of AI, I think a very brief history would be like this. The first attempts, like from Alan Turing and later, were one level. People thought, we could just program everything in a computer. We'll just put if-then rules, and the programmer will do the type it in, and then the computers will do it. Soon enough, it became clear, well, it's not going to work. The combinatorics is too big. So the second improvement was, okay, let's go one level below, and we don't program everything into computer. We actually program a few learning rules, and then give big data to the computer, and then the computer will learn from the data. That's much better, much more adaptive. But what Practopoiesis tells us, the theory, and then application of the theory to what we know about the human mind, is that we have to go one step more down. We have to make one more big step down, and then we can get to that level.
So we have to teach the machine how to learn. So that it can learn to learn on its own and then go and learn.
Something like this, yeah. It's a bit confusing when you using this terminology. That's why I introduce some other words like for this process.
Okay, so create rules of learning on how to learn, and then go and learn.
Yeah, that's pretty.
All right, very good. So now you mentioned one word there that I want to grab, and that's the word consciousness. Where does consciousness fit within your model? Or does it?
It fits very nicely in the model. Right? There is this big problem with consciousness, big discussion with consciousness, lots of different views. And if you look from the perspective of cognitive scientists and some of the philosophers, not everyone, They would say, well, you neuroscientists still did not explain consciousness. You didn't do good job at all, and there's a lot left to figure out. Then you have perspective of neuroscientists who would say, no, we have figured out, everything works, and the consciousness actually doesn't matter because the system works.
Yeah. Peter Voss, who is actually one of the people, the two people together, I think, with Ben Goertzel, they coined the terms narrow and general AI, and who works in the field. He said, he shocked me during my conversation with him. He said consciousness is a solved problem.
Yeah, he's not alone. There are many people, also in neuroscience, there are many people who think this way. Right? And now, when you look at T3 systems with 3 levels, then this confusion becomes somehow cleared up. And what it turns out is that people who were saying, well, you need consciousness have been right, but also people who said, well, we don't need it have been right. But they were talking about 2 different systems. In a T2 system with 2 levels, everything works fine, you don't need a consciousness. But this system cannot do the adaptive kind of things that humans do and animals do. The people who are saying, well, you didn't get a consciousness, they were looking at the behavior, what's happening in T3 systems, the systems with 3 levels. And it was just not clear what was missing there. And now practopoietic theory actually suggests what was missing. And then consciousness can be, I wouldn't say explained very quickly and easily, but we can start, we have a very clear point where to start.
Where it fits.
Where it fits. It fits actually in the middle of these 3 levels. So you have a low level, learning how to learn, very general learning rules. Then you have your learning rules up that you learned over life, many learning rules, your knowledge in this learning, and then you have the network activity. So the consciousness will be here in the middle, this new process that neuroscience did not consider so far. This process of restructuring your network quickly within half a second or a couple of hundred of milliseconds. This process that hasn't been really recognized as important is actually the one where we have to understand better, study it empirically, theoretically, and that's how we are going to make progress in understanding consciousness.
Another word that you said here that I want to grab is empirically. So let me ask you this. Can we test and or allocate those layers in different parts of the brain by an empirical observation or test? Or in other words, can we associate those different levels with different brain tissues and or areas?
Yes, absolutely, definitely. Of course, 2 out of 3 have been studied quite a bit, and we have a very extensive knowledge of those. And the question is, of course, with the third one. Where is the third one? And since it's a poietic theory, predicts that it must be actual mechanism. It must be actual separate physiological machinery that does it, because it has to be able to poetically create some other machinery, and it has to be created by some other third machinery. Where it is located right now, I don't know. We don't know because we have to start doing experiments. However, it's important to realize that there is a lot of mechanisms, lots of physiological phenomena and mechanisms and machinery in the brain that we have seen already in experiments, and that we have for all these years ignored, gave them minor functions, or did not put them in the major theories of how the brain works, exactly for the reason we didn't have a place for them. We didn't know what to do with them. They were there, they were under the microscope, they were there when we recorded the activity of the brain, they were all the way there. They were actually all the time yelling to us, hello, I'm here, come on. And then what we did with them, we didn't have the right theory, so we did then, again this problem, again this noise. Let's average it out. Let's come up with an experimental design to get rid of these things, because they make no sense to us. So we were actually kind of putting under the carpet data that were telling us, look, here we are. This is what's happening in the brain. And now we have to basically look at it, study it, probe it like we do empirically, and we will learn more about them. And we'll probably soon locate these mechanisms.
Mm-hmm. Do you think we will be able to locate consciousness?
In a way, yes. I mean, all these mechanisms, you can at the end find the physiological processes. And then once we agree on a definition where we put the border, what is conscious, what is not, then we can say, okay, this and this and this mechanism is responsible for that. This other is not, but it's supporting it that way. So we will be able, and the confusion, the mystery, I think will kind of go away. I think of it as a magic trick. When you see some amazing magic trick, and you don't know how it works, it's perplexing. Yeah, it drives me crazy. You think, oh man, you think of all kinds of crazy things, but what happens when you find out how it works? It becomes trivial. It becomes uninteresting in a way. It loses this glare of mystery. It loses this glare of something being fantastic. And that's why magicians don't want to give away tricks, because people are not interested anymore about tricks that they know answers to, so they wouldn't make any money. I think something similar will happen with the problem of consciousness, that we will understand these mechanisms, and the concept, the word consciousness, will lose quite a bit of scientific meaning. It will still stay in popular language, of course, but scientifically it will lose meaning, and because we will differentiate in many different additional mechanisms and so on. So I think we will solve that problem.
So speaking of sort of popular consciousness or the public perception, let me give you a quote from David Brooks from the New York Times and ask you to comment on it. So he says, "The brain is not the mind. It is probably impossible to look at a map of brain activity and predict or even understand the emotions, reactions, hopes, and desires of the mind. So the next time somebody tells you what the brain scan says, be a little skeptical. The brain is not the mind."
All right. If he puts it that way, so he says brain is not the mind, and then defines how it is, I think it's correct. I think it is correct. It's just, if you would have, somehow completely 100% accurate scan of the brain and know every molecule where it is, you couldn't tell anything about the emotions and what this person is thinking and so on. So this is correct. The mind is built on these physiological mechanisms, but there is a huge complexity gap that you cannot go from these molecules to the mind and directly understand it. So this is like, let's see, in the case of theory of evolution, if you look just all the molecules in a certain, let's say, bacteria, I guess you couldn't be able to tell many things about how this bacteria lives its life, what does it eat, how it survives, what kind of, I don't know, dynamics, physiology it has. It's also complex. Maybe it's not as complex, but still a complex problem. So it will be saying, okay, molecules are not life. That's true. Molecules are not life, and yet life is based on molecules. Same thing here. A brain is not mind, but yet mind is based on this brain. And there is this complexity problem that we have to solve, and we solve it by various scientific theoretical tricks, like theory of evolution, like theories of metabolism. And I think practopoiesis will be one useful way of solving this complexity problem.
Another way of solving, or not solving, but sort of proposing a theory of consciousness has been pushed forward by Dr. Stuart Hameroff and by Roger Penrose. the so-called ORC, or quantum theory of consciousness. What's your take on that?
I'm not really buying it.
Why not?
I have read about it since a long time ago. It's been around quite a bit. My opinion on this one is that it's not explaining anything. It's like you have two mysteries. One mystery is consciousness, complicated to understand, difficult to grasp, and the other mystery is quantum mechanics, complicated to understand, difficult to grasp. Don't know what's happening, which interpretation of quantum mechanics we should take. So they say, okay, let's simplify and make these two mysteries one mystery, and this mystery and this mystery are one mystery. Doesn't explain anything. Even if it was, let's say, if it was correct and if it was true, I would be very disappointed because it wouldn't explain anything. I wouldn't know anything more about the brain before and after this theory. It's just saying like, it's just complicated. It was complicated, remains to be complicated, remains to be incomprehensible. So it's very, doesn't produce epistemological satisfaction.
But does that mean it's not true? And also, I mean, it's been probably well over a year since I interviewed Dr. Hameroff, but I think just one of the probably not so excellent examples was that their theory, for example, can take into or can propose a way of explaining extra body experience of people who are unconscious, for example, and who describe the room that they've been in or something like that.
Yeah, I could imagine how this theory could explain something like that, but a theory like this should explain many more things.
Let me give you a better example. I think now it's coming back to my mind. So, for example, when people take certain kind of, was it the DMT, the molecule that you find in ayahuasca and all other hallucinogenic substances, right? And the classic model of the brain would suggest that if you're having those experiences and people are reporting them, all kinds of visions, colors, etc., the brain has to be all lit up and active. And yet what we observe is quite the opposite, quite the contrary. It looks like when you look at it from an fMRI point of view and so on, it looks like there's not much going on happening there. And yet people are having all those very vivid, very powerful experiences, which do not seem to be registered by the brain. So therefore, the argument goes, they must be happening at some other level, like the quantum level, at which we cannot detect them, or they're kind of plugging into that quantum level.
I mean, this argument is logically consistent, but it remains to be a very weak argument because, see, any theory in neuroscience has to not only explain this one thing that you're not explaining, but it has to be consistent with a vast knowledge in neuroscience that we have collected over many years. And you can have, that thick books, and then another thick book on the behavior and psychology. It has to be all generally consistent. And that's where such theories fail. They explain one phenomenon and are largely inconsistent or at least ignorant of many other facts. You wouldn't know how to put anything from a textbook into this theory. And you explain one thing, you unexplain or kind of make a problem, a conceptual problem for hundreds of other places.
Mm-hmm.
So, and that's not really, good. It's not really attractive as a theory.
Well, it may show us that we don't know as much as we think we know, and that we may have to reevaluate, and that certainly is uncomfortable. But in some cases, just like Einstein did, for example, like we had to reevaluate everything after him. But let me move on to the other sort of a big problem here. One is consciousness, the other is free will. So
Okay.
You're laughing. Are you? Do you not agree that that's another sort?
No, no, it's perfect. It's perfect. I'm kind of glad that you asked this question. They're very popular, interesting questions. Yeah, it's.
So where does free will fit within your? I mean, they're popular, especially and important for me because, uh, from an ethical point of view, I would like to believe that we are free agents, and we possess the power of free will. So let me ask you, where do you stand on that continuum? Because an awful large number of scientists that I interview on my show have been determinists to one degree or another. And also, once you tell us where you are, then perhaps whether and how free will fits within your practopoiesis theory, or does it at all?
I'm a determinist as well. So free will, the experience of free will, the illusion of free will is something that comes out of deterministic physical processes. Nevertheless, I think we should feel like we have a free will. We should enjoy this feeling, and we should treat it as if we have a free will. And I think the reason for that is that Practopoiesis gives us so much flexibility, this T3 system, and so much capability of adaptive behavior, and it gives us gives the system the ability to adjust and learn how to adjust more and more. That if we treat ourselves as having a free will, we will actually progress more and become better and better and more successful. So I don't think it's a problem that we are deterministic. And now, where does it fit in the practopoietic theory? As we discussed a couple of minutes ago, there is this practopoietic theory of T3 systems, or three-level systems, presumes that all our knowledge is stored one level below, in very general rules on how to interact with the world, instead of having exact rules on how to interact in different situations. These general rules come up in our mind as something that we call concepts and conceptual understanding of the world, all kinds of concepts. As we develop, as we learn the world, we learn concepts. Now, to understand the free will, we have to understand the type of concepts that normally a human develops. And there are some very important concepts for us, and one of these concepts is the concept of self. Me, I, is a concept. And then there is a concept in the contrary, the rest of the world. Now, as we develop as a child, throughout our life, we sharpen this distinction. What is me? What is the rest of the world? And as we go, we learn more and more the my part, the world part, the relationship between me and the world. And by developing this rich structure of conceptual understanding of the world, that's where we start understanding, dissociating ourselves from the world, and that's where we start getting the feeling, the experience, and also practically it works that way, that we have quite a bit of a free will of decision how to interact with the world, right? And so it's the richness of the conceptual structure that we develop at this low level of organization.
What you're saying would, in a funny way, kind of support the Zen Buddhist idea that distinction between us and the environment is an artificially created one. It's not a real one.
Absolutely. Absolutely. The concepts are something that's practical, that's useful. It's not absolute truth. It's something and it's really practical to think of myself as myself individual, because whenever I move and go somewhere, everything else goes with me, right? If I go there and into another room, also my hair will go with me, and also my knowledge, my skills, everything will go with me. So it's practical to think of me as one entity. If you could possibly try and think a different way, and you'll probably end up confused and making errors and mistakes and not be so adaptive in your behavior. It's just a practical thing. It's not an absolute truth.
Mm-hmm. That's absolutely fascinating. That's absolutely fascinating to me. Danko, so Let me give you another couple of examples here. We've already discussed about the Orch-OR theory, but what about the Human Brain Project? How do you think and where do you think that fits in our ability to garner new knowledge, or the connectome, the Human Connectome Project? I think that's the parallel in the United States, if I'm not mistaken. So, what do you think of those projects?
Well, both of these projects are based on the two-level presumption.
Yes.
And if that were the case, if T2 systems is exactly how the brain works, then yes, we have some conceptual problem, because we have this theory and we don't get it really how the whole thing comes about from these pieces. And in this case, it would be reasonable to make either of these steps or both of these steps as another attempt to figure out what's going on, because we cannot do it analytically. We've tried for so many years, so let's just put everything, simulate in a computer, one way or the other, two different approaches. But
massive amounts of data.
Massive amounts of data, put it in a computer, press the on button, see what happens. And then maybe we'll learn something more. It has been shown in the history of mathematics that this has helped. If you put you take some differential equations, some chaotic systems, you simulate them, you learn something more about the system that you couldn't do analytically. So it would be kind of reasonable if it was a T2 system. But as my opinion is that the system is a three-level system, I think they're completely missing out. They are going to simulate all these parts that are incomplete at the end, and they will look at the complexity of some computer simulated machinery that is very complicated and yet incomplete, like seriously incomplete about what the brain really does, because it's missing one very important component.
Mm-hmm. That's very interesting, because that's kind of very much what Professor Marvin Minsky said during my interview with him. He thought it's an enormous waste of resources, precisely because of the fact that they did not start or have an overarching theory of how the whole thing would work together.
Yeah, exactly. Maybe it's an overstatement, but it kind of looks like a desperate move. Like, we don't get it. Let's just try something crazy. Let's just put everything in the computer. Maybe the computer will get it for us. And I had this morning a discussion with some friends here at the Institute. And one pointed out, came up with explanation that it's a lack of patience. Maybe. Instead of going theoretically, patiently through some steps analytically, maybe I just put it in the computer, and then the computer will do the work for us. So I think these projects are certainly going to be helpful in some way. There will be something will come out of it. It's not like a complete mistake. Something will come out of it. We will know after something more than we knew before. But I think they're not going straightly for the reward. They're not going straightly to the point. There is a quicker way, I think.
So let me ask you this then. So if they're missing kind of a major element here of the whole sort of hierarchical structure of the brain model, then what does that say about the potential for mind uploading? Because those two projects can be qualified as, in a way, whole brain simulations or attempts at whole brain simulations. And you're saying they're not going to work very well precisely because from the get-go, by design, they're missing a major component.
Yeah.
Then also we have attempts by people such as Randall Kuna to create whole brain emulation. So what does Practopoiesis tell us about the possibility or the potential to create mind uploads?
It's going to be very hard.
Harder than we think.
It's going to be this amount of knowledge that you have to have at this level. This is so many details, and they all depend on each other. It's really, really hard. It's like, scanning a book, but you don't want to scan the letters. You want to scan all the little pixels, everything correct. And if you get a few wrong, it's not anymore your mind. It's some other mind. And it could mess up things in some way. So it's going to be, I think, really, really hard. You would have to have some very precise machine that can get, every molecule down to the precision that, doesn't really matter. The error doesn't really matter. And then once you've done it, once you scanned all this, you have to simulate it and run it. And then you have to have this supercomputer. And then, if you may be able to do it from one mind, what's the point? How you going to do it for multiple minds? How are you going to make it commercial that anyone can buy it?
Mm-hmm. Accessible, yeah.
Accessible. I don't know, maybe, but it's really somewhere far, far, far in the future. We'll need several major technological advancements. But in principle, it's doable so right now as a science fiction technology.
Danko, I have to say I've been enjoying immensely our conversation here, but unfortunately time is advancing and we've been chatting away for over an hour now. So let me ask you the second last question that I usually ask, and that is very simply, where can people go and find more about you and your work? What's the best place?
Well, it's very easy to find my website. Just Google my name. The first link will be my website. Google the word Practopoiesis. You will find all the information. Then everything's linked, and it's very easy to find it.
Mm-hmm. Very good, excellent. And of course, I would link from our interview page. And now we're coming to perhaps the most important part, and that's the final message. That after speaking about a variety of sort of topics for 60 minutes, what do you think is the most important message that you want to send out for our viewers and listeners today?
Well, what I would like to say is the following. We normally think, neuroscientists, computer scientists, engineers, that we have to understand the brain, the intelligence from the point of view of information processing. We have this one-level system that contains information and it jiggles this information somehow and the result comes out, like our computers. This is the paradigm to understand the intelligence. And what Practopoiesis says, no, it's not the paradigm to understand the intelligence. It is required, it's the necessary component. But where the intelligence and the mind really comes about is about the mechanisms that in real time, real fast, reorganize this system that contains information, that actually build the properties, that create the properties of this system. And the creation of the system is what we have to look after, not the information. Information is the easy part, and creation is the hard part that we overlooked so far.
That's absolutely fascinating. Danko Nikolic, I'd like to thank you for being with us today.
And thank you very much for that too.